Training LLMs with reinforcement learning means running multiple models. Some have different sizes, some require training while others stay frozen, and some might share GPUs. Frameworks like veRL, Volcano Engine for reinforcement learning, developed by ByteDance, handle this for you. But what's actually going on underneath? That's what this series is about. In this video, I'll walk you through three things. First, we'll go through the PPO pipeline. It will serve as a concrete example to motivate what we'll be doing. Then, we'll map that to hardware, and we'll show the different constraints we have to work with. Finally, we'll talk about the single control pattern, the one driver process orchestrating everything. By the end, you will understand why frameworks like veRL are built the way they are, and what we are going to build ourselves from scratch. So let's start with the PPO pipeline. Let's start with our input, which is going to be prompts, a data set of prompts. These are going to be fed to a rollout engine. It can be VLM or SGLang or anything else that you are comfortable with. The rollout engine is going to give us responses. And what we care about are the pairs of prompts and responses. Because these, the responses and the, or also called generations or rollouts, along with the prompts, they're gonna be fed to four consumers. Four consumers in the case of PPO. It can depend on the algorithm. It's gonna be three in the case of GRPO, for example. So, sorry, I had to cut because I found that I didn't have enough space. But then we can start with the reward model, and this one's goal is to score each prompt response pair, and will give us a single scalar score that qualifies how good is this response. So this model is frozen. It was trained on human preferences beforehand, and we don't touch it during our PPO training. And then we have the reference policy. And the reference policy is the same architecture as the actor, and as a matter of fact, probably the same weights, but frozen at the start of training. Think like the XFT checkpoint, or maybe a sub between different checkpoints during SFT. And it gives us per token log probabilities under the original policy. We need this to compute the KL diversion so we don't drift too far from it. It's also frozen and never updated. As a matter of fact, maybe we can do them, color them in some kind of icy blue to say that these are frozen and never updated. And then we have the actor here. This is what's gonna take the most out of us. We'll see why. But the actor is the policy we are actively training. It also gives us per token log probabilities, but under the current weight or under the current policy. The gap between the actor's log probes and the reference policy's log probes is the KL divergence signal. This one is trainable and it's getting like brilliant updates and everything. We have the critic, which is trainable as well, and this is our value function. We can actually color them in orange to say that these are hot and getting updated. And the critic is a learned value function. It estimates how good is this state or how much reward do we expect from the current state onward. This is specific to PPO, and for GRPO it doesn't change the critic, and it estimates the advantages differently. So you see that we already have to orchestrate between all of these different components. Granted, PPO is slightly complex, for example, as compared to GRPO, which we drop this training component here for the critic, but complexity is still there. And so the outputs of all of these, they go to the driver. And the driver, it can run like on CPU, it doesn't need GPU, and we'll delve more into what driver is, etc. But here we're gonna compute the KL divergence, we're gonna compute the rewards, and this is the generalized advantage estimation. And from these we get two things. We get the advantages and the returns. The advantages and returns go back to the actor and critic for the PPO updates. I put it like this. The actor minimizes the clipped surrogate objective, while the critic minimizes MSE between its predictions and the actual returns. And both update their weights since they are trainable. And now we need to think between the actor and the rollout engine. After the update, the actor's new weights get synced to the rollout engine, so the next batch of generations come from the latest policy instead. And we'll talk about this a little bit later on. So that's one iteration, and everything gets repeated, obviously, during this whole thing. It's a loop. So this is PPO at a very high level. It's quite complex compared to other algorithms, but there are other algorithms that are easier. Obviously, for example, GRPO, as we said, it drops critic entirely, and instead of learning a value function, it generates a group of G responses per prompt and normalizes the reward within the group to get advantages. But yeah, so we have 4 model roles here, different models, different roles in PPO, or I should say 5 for PPO if we include the rollout, and 4 for GRPO. So the orchestration complexity is still there. Now, besides the orchestration challenge, let's look at some other challenges. Let's put these different PPO components into hardware. We'll take a very simple and toyish use case for illustration, but we saw that we have 2 different models here that need training and 2 here that are frozen. But there's another difference, it's the size. So the actor is your big model, and the reference policy being the same as the actor is also very big. So think a 7 TB model or something. While the reward model and critic are in general very small. In practice, the critic is initialized from the reward model, but it's not a requirement, obviously. So different sizes, different architectures, and different modes, training and inference. And this is a very important thing because training and inference have 2 different memory profiles. For inference, we need to have the weights, KV cache, and the activations, but for training, we need the weights, the gradients, the optimizer state, and the activations. And for example, if you do mixed precision training with Adam W, for example, you have BF16 weights, you have FP32 master weights, you have BF16 gradients, FP32 momentum, FP32 variance. So that's 16 bytes per parameter, and this is without accounting for activations, which scale with batch size and sequence length. So it can be a lot, or like very heavy in terms of memory, while inference is not that much. So for example, this leads us to different parallelism strategies. For inference, in general, just tensor parallel is just enough, but for training, you might need combinations of different parallelism techniques like FSTP and TP and PP, etc. So this impacts something called colocation. So what is colocation? The word is self-explanatory. It means that in the same location we put different stuff. So in the same node, or maybe using the same GPUs, we'll share them and use different models. But from a practical standpoint, these different models, they need to have the same architecture. So for example, the actor, the reference policy, and the rollout, they can share the same GPUs. The critic and the reward model, they can also share the same GPUs. I don't think it's... So there is a trade-off for making rollout and actor share the same GPUs, because you can turn them at the same time, obviously, and that makes like your whole infrastructure idle. While you are doing training, you can't do generation, and while you are doing generation, you can't do training. So in general, they put the rollout engine and the actor as separate. Obviously, then you have some kind of staleness, but PPO, the importance ratio, that's correct for that. So what happens for the weight syncing is that while you are doing the backward propagation, while you are updating the weights, you're gonna start sending them to the rollout engine, and that's to optimize like computation, to overlap computation and communication. So let's put that into some very simple diagram. Again, it's just toyish examples. Obviously, I think 3 nodes are not enough for a 7TB model, but let's say you have a node here with 8 GPUs. You can fit in both or like collocate both the reference policy and the actor. The reward model and the critic are smaller, but obviously, as I said, you probably need more GPUs like for the training itself. Let's say you have the reward model here and critic, and this is for the rollout engine or rollout engine. So this is going to always work in TP. The reference policy as well, it will run in TP. Similarly for the reward model, or maybe the reward model might even be small that you don't even need to parallelize it. But for the actor and the critic, it's going to be a little bit tricky. So how this is going to work, for example, in this case, in one iteration, is that the actor or here these GPUs are going to do multiple things. So the reference policy forward path to get the reference log probs, and then you need the actor's forward path to get the new policy log probabilities. This might be in TP, and then what we are going to do is reshard from TP into something else like FSDP and I don't know, pipeline parallelism and whatever you want. So that's why I said probably you're going to work with many nodes. But yeah, and so swapping from like if you are in TP and it's the same architecture, it's just swapping from different weights, so different active weights. But obviously resharding is a little bit costly. And then you have syncing here where you have to send weights over the network. So there are some costs for network operations. But that's also a challenge to know when to reshard, when to send weights, etc. So we see here that we have a lot of components. Different components will be in different layouts. We have to swap weights. We have to send them over network. We have to send to different components the data. We have to collect it. The data will be heterogeneous. And all of that will be driven by the driver, or also called the single control pattern. So what exactly this will look like in the driver, if I can duplicate that. Okay, my bad. So what the driver will do is just like hold the training loop, and it's going to be like very simple, like simple PyTorch training loop that you know for like for batch in data loader, etc. And the driver, it knows the data flow, like when to send what data to what component. Obviously this goes through like dispatch strategies, etc. And then it knows how to collect the data. For example, like we can write a very simple training loop for this if you want, in like some kind of pseudocode. Maybe I can create a new block. So it can be something like for batch in dataset or data loader, and then you have your responses are gonna be like send the this batch to the rollout, and these responses are going to be sent to the reward model, to the reference policy, to the actor, and to the critic. So each one is gonna give you different stuff. So scores, we get them from the reward model. It's gonna be like some method called score, and similarly we'll get the old log probs and the new ones. So this is by ref, and this is actor compute log p, and we'll see that this shows the notion of worker groups. So we'll see more of that later on, but yeah. And then you have the values. So it's for the critic, and then the driver is going to collect all of that. So all of this complexity is abstracted away by the driver, but we have to implement it obviously, and it's a dispatch layer or the orchestration layer that we'll be implementing over the next videos. But then you have something like advantages and returns, compute generalized advantage estimations. So you can take the scores, values, ref log p, and a new log p. And then what we're gonna do, obviously, we have to update advantages, and then here we're gonna do something like returns. Obviously, we're gonna see all of that. We're gonna build it across throughout the videos, obviously, and also the orchestration layer itself. That's the most important part for us, and then you're gonna handle the syncing of as well. But yeah, so hopefully you see the need for the single control pattern and how the different components they crystallize this need. So for example here, when we do ref log p equal ref dash compute log p, what's gonna happen is like this is it will be a worker group. So for example, this one is gonna be a worker group. The worker group is a set of GPUs, each and having different workers on different GPUs. So for example, a worker for the reference policy on a GPUs here, and the actor on maybe different nodes as well. And it goes like so. So yeah, the driver doesn't talk to individual GPUs; it talks to like groups of workers. And it goes like you, the actor, you have to compute the log pros on this data. You, the rollout, you have to generate from these prompts, etc. And so this is here. And the worker group, it knows how to handle the splitting across its GPUs. So for example, if you are doing training, you're gonna send different data shards to different data parallel groups, and within the same TP obviously group you have the same data, right? So the worker group, it knows all of this, and it's just like the driver here is very easy to write, and these can be synchronous operations. They will be sent and executed on different processes across different nodes. I hope this was clear. So this is the big picture for RL post-training. It involves multiple models. PPO has 5 roles, GRPO has 4. It can be something else, maybe with different other algorithms. But yeah, each model has a different size, a different mode, and different GPU needs. So mapping them to hardware introduces colocation, resharding, data routing challenges, etc. Obviously, you don't really need colocation. It's just one other concept that you can introduce. You just show different complexities. If you're not doing colocation, you need all of these different elements living on their own GPUs, and then also you have to still orchestrate between them, right? And I hope that you see that the single control pattern is an easy way to handle this complexity, because you can write your training loop very simply, and the complexity is abstracted away in the orchestration layer in and of itself. So over the next videos, we'll build this orchestration layer part or brick by brick, and we'll use Ray as our distributed runtime or framework. So we'll build the whole orchestration layer from like workers to dispatch strategies and worker groups and resource management and colocation, etc., until we have a working module